my most favorite chapter of all of the chemistry chapters. Nuclear chemistry. So get those black notebooks out. This is going to take about 2 weeks to do, and the stories are phenomenal in this chapter. Absolutely phenomenal. So it says nuclear chemistry. So it must have something to do with the nucleus. So this is just review for right now. Don't forget, the nucleus has 2 subatomic particles in it. The protons and the neutrons. Now, reference table O. In your reference table, it says symbols used in nuclear chemistry. It has these right on there. So for protons, it's this. P11 or H11 plus. Either one of those you can use for a proton. And remember, protons only found in the nucleus, they have a positive charge. They're found in the atomic mass, and they're also found in the atomic number. In fact, protons make up the atomic number of an element. And remember at the beginning of the year, I said you could change the neutrons, you can change the electrons, but you can never, ever, ever change the number of protons, or else the element would change. Well, that was true all the way up until this chapter. Now on this chapter, something weird is going to happen to the protons. All right, so that's protons. Neutrons. Neutrons, N10, which means the neutrons are found in the atomic mass, but they are not found in the atomic number. Okay? So neutrons found in the atomic mass, protons found in both atomic mass and atomic number, and electrons, they're not in the nucleus. So we're not really going to talk about them right now. Now, next thing we're going to talk about, we have to talk about this before we get into the good stuff, is this. Isotopes. We did this like the first month in September. Isotopes. Here's what it means. So in other words, an isotope has to have the same number of protons, but a different number of neutrons. So another definition of isotope. So you have 2 definitions of isotope. Got the same number of protons, different number of neutrons, or the same atomic number in the lower left, but a different atomic mass. Those are the 2 definitions of isotopes. Also, if you remember me telling you that every element has at least 3 isotopes. Every element has at least 3 isotopes. So let's do the first one. The first element is hydrogen. And let's just do the 3 isotopes of those. So don't forget, H11, H21, H31, do they abide by the isotope rules? Yes. They all have the same atomic number, which means the same proton number, but they have different atomic masses. So let's look. This has 1 proton, 0 neutrons. This has 1 proton, atomic mass is 2, got 1 neutron. This one, 2 neutrons. Now, here's the deal. Every single element, I told you, has at least 3 isotopes. And of those 3 isotopes, 1 is considered to be radioactive. Now, you don't know what radioactive means yet, but it's got to mean something strange. So for these, H11, H21, H31, this one, H31, that's the radioactive element. So radioactive elements, I'll tell you a little bit, something is going on with the nucleus. And if something changes in the nucleus, chances are the element may change if the proton number is messed around. So, every element has at least 1 radioactive isotope. It's sometimes called radioactive isotope, but mostly it's called radioisotopes. So we will be discussing radioisotopes. Next one. Remember, I said I don't like the elements written that way, but that 015, 016, 017, that's the atomic mass. Okay? So the way I like it written is you put the 15 here, the 16 there, and the 17 there. And since it's oxygen, oxygen has the same number of protons, so it's 8. 8, 8, 8. And then if you want to find the number of neutrons again, subtract, subtract, subtract. So we have 8 there, 7 there, and 9 neutrons there. Now, of these 3 isotopes of oxygen, the radioactive isotope, or the radioisotope of oxygen, is this one. O15 is radioactive. So that must mean, like I said before, something is going on in the nucleus. Okay? All right. Now, this is what you're going to put in your black notebooks. That was just review. So, we're going to put down Roman numeral 1. Natural transmutation. Now, you've never heard of the word transmutation before. But trans means change, and mutate means there's a change. So, transmutation just means something is changing into something else. Okay? Natural means it does it by itself. Natural transmutation. So, here's the definition. We'll write it down. When one radioisotope So, natural transmutation, when one radioisotope changes into another radioisotope. Well, how does one isotope change into a different isotope? Well, if it changes into a different element, that must mean something happened with the proton number. And that's the whole deal about transmutation and radioactivity. It's all about protons. What happens? They change. And if the proton number changes, the element changes. Okay, so when one radioisotope changes into another radioisotope, that's the first thing. For number 2, there are 3 types of natural transmutation. That's what I want you to write down. There are 3 types . 3 types of natural transmutation. Okay? Now, before we do those 3 types of natural transmutation, we have to talk about the periodic table. And I'm going to just shoot the video over to the periodic table. Don't forget, the periodic table is arranged in order of increasing atomic number, which means it goes by the number of protons. Now remember, a proton's positive. And the deal is this. As we get, like manganese has 25 protons, and we keep on going, protons are positive, and they're packed in a small area. And remember, likes repel. So they don't really want to stick together. And by the time we get down to atomic number 82, which is lead, of the 3 isotopes of lead, 2 of them are radioactive and 1 is stable. All right, so lead has 2 radioisotopes and 1 stable one. Because remember, that means there's 82 protons and they don't want to be there. So they start shooting out of the nucleus. Okay, the very next element, bismuth, that all 3 isotopes of bismuth are radioactive. So what I'm telling you is this. The last non-radioactive element is lead. After atomic number 82, all the elements after atomic number 82 are radioactive, which means all of their isotopes are unstable and they spit out protons. So they're all radioactive after atomic number 82, which is lead. Okay? All right, now one more thing. Atomic number 92 is uranium. Notice that's the last element that's totally dark, totally colored in. That's because it's the last naturally occurring element on the periodic table. After uranium, all these elements are man-made. Okay, so uranium is the last naturally occurring element on the periodic table. All right, now, knowing that, now we'll get back to the 3 types of natural transmutation. Now, like I said, there's 3 types of natural transmutation, and the first type has to do with these things, alpha particles. You heard of alpha particles before. Yep, you did. Rutherford's gold foil experiment. He shot alpha particles at gold foil. So here's a short video on the gold foil experiment by Rutherford, put in by Atomic School on YouTube.
An extroverted New Zealander with a booming voice and a big laugh. Rutherford was playing around with beams of positively charged particles, which he called alpha particles, that were emitted from uranium atoms. He knew they were positively charged because they bent in the opposite direction to the electrons of a cathode ray when passed through charged parallel plates. They bent more slowly than electrons, so he knew they were heavier than electrons too. Rutherford used these alpha particles as atomic bullets and fired them at a very thin sheet of gold that was only about 1,000 atoms thick. On the opposite side to the uranium source, he placed a scintillation screen that lit up when particles hit it, so he could then measure where the alpha particles landed. If the gold atoms were like billiard balls, then the alpha particles would be blocked and none would arrive at the screen. Instead, almost all the alpha particles passed straight through the gold foil as though it wasn't there. Rutherford realised that the gold atoms were mostly empty space. J.J. Thomson thought that the mass of atoms was pretty evenly smeared out within the substance, and he also thought that most of the alpha particles would pass through. But something very surprising happened. Some of the particles were bent a few degrees off course, and about one alpha particle in 20,000 bounced right back in the direction from where it came. Rutherford said at the time that it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. What this meant was that the mass of the gold was not evenly spread out at all, but concentrated in very small lumps that were positively charged. He had discovered the atom's nucleus. Because the nucleus was so small, most alpha particles didn't even come close and completely missed them. They went straight through. If some went close to the nucleus, its positive charge would cause repulsion and bend them off course. If an alpha particle made an occasional direct hit, it would bounce right back from where it came, because the nucleus was much, much heavier than the alpha particle itself. The nucleus is incredibly heavy. Over 99% of the atom's weight is concentrated there, and incredibly small. If we magnified an atom to be the size of a football stadium, the nucleus would be the size of a pea. Rutherford later discovered a particle inside the nucleus that was responsible for its positive charge, and he called it the proton. An atom's overall nuclear charge was equal to the number of protons it had in its nucleus. And this also turned out to be the same as the atom's atomic number. Each element had its own number of protons in its nucleus. How's that for a coincidence?
Number one, under alpha particles. Here's what an alpha particle is. He42 plus 2. That means an alpha particle has 2 protons. 4 minus 2 is 2. 2 neutrons, but it says a plus 2 up there. So an alpha particle's got 2 protons, 2 neutrons, but no electrons. So an alpha particle is this. It's simply the nucleus of a helium atom without the electrons. That's what an alpha particle is. Okay? All right. Now, what that means is some radioisotopes spit out alpha particles. And if you spit out something that's got 2 protons in it, it's got to change what the element is. So, there is a handy-dandy chart. And the chart is reference table N. And this chart tells you what radioisotopes spit out alpha particles. So an alpha particle, another way of showing an alpha particle is, looks like that. I always say it's like a fat fish swimming to the left. So that's the symbol for an alpha particle. And on reference table N, it shows some of these. Alpha emitters, they're called. Now, so what's the big deal about an alpha particle? Well, first of all, it's got a positive charge. Alpha particles got a positive charge. They've got a mass of 4 AMUs. So, the way I look at an alpha particle is this. Compared to all the other particles that are shot out of the nucleus, this one's the biggest. So when you think of an alpha particle, I want you to think of a bulldozer. And you know bulldozers are really big, but they go very slow. Okay? So, watch. If I had a radioactive element on the tip of this, and it was an alpha emitter, I could hold it just like this, and I wouldn't get hit by any alpha particles. Because alpha particles only travel several inches before they dissipate. So, for number 4, why don't we go metric? They only travel several centimeters. Okay? Number 5. Well, let's do this. Number 5 is they can be stopped by skin or clothes. Stopped by skin or clothes. So they don't have very much penetrating power. So if I held an alpha emitter like this, chances are it wouldn't do very much to the person. But I have a story coming up later on about alpha particles and my sister. Okay, so stopped by skin or clothes. I put down number 6. We're going to leave that blank right now, because the next thing we're going to do is called alpha decay. All right, and that is going to be an asterisk. Now remember, what I said is, if I had an alpha emitter radioisotope right here and I held it like this, it wouldn't even hit me. And if I brought it here, chances are it would be stopped by skin or clothes. Okay, so are they harmful to people? Well, let's talk about that. On this sheet, on reference table N, one of the alpha emitters is this. Rn, that's radon, 222. So let's see what the atomic number of radon is. It's 86. So, now listen. An alpha emitting radioisotope means it spits out an alpha particle. So watch. Rn 222. That radon is an alpha emitter, so it throws out an alpha particle. So what's left? The masses on the left have to equal the masses on the right. The atomic numbers on the left have to equal the atomic numbers on the right. So look, that 222 lost 4. So now we're down to this 218, and that 86 lost 2 protons, so that goes to 84. And the new radioisotope is called polonium. Okay, so watch. What do we know about this? An alpha emitter means that it emits an alpha particle, and what happens is the atomic mass of the alpha emitter goes down 4, the atomic number of the alpha emitter goes down 2. So down 4 and down 2. But why did I give you this particular alpha emission? Because of that. Radon. Radon is in group 18. All the elements in group 18 are gases. So radon is an alpha emitter. And in our area, in the southern tier of New York, we don't have very many hurricanes or tornadoes or earthquakes or fires or anything like that, but we do have radon in the ground below our houses. And radon is dangerous. But I just said alphas, they can be stopped by skin and clothes, but radon is a gas. So if you breathe it in, the radon gas would go into your lungs and start firing out these alpha particles. There's no skin or clothing down in your alveoli sacs, the sacs that exchange gases. And so what could happen is, if an alpha particle slammed into one of the cells in your lung that was starting to reproduce by mitosis, it may smash that mechanism of reproduction, and the cell may reproduce and reproduce and reproduce and reproduce. That's a tumor, and that's cancer. So, radon is very dangerous if you breathe it in, because it could give you lung cancer. Okay? All right. Now, before we go on, I told you I had a story about my sister and alpha particles. So, let's do another one of these alpha decays. Okay, so this is the next alpha decay we're going to go, and if you look on this reference table N, it says that radium is an alpha emitter. So any alpha emitter, poof, coughs up an alpha particle. And remember, if it's an alpha emitter, mass goes down 4, atomic number goes down 2. So this mass is 222, and that goes to 86. And 86 happens to be radon. So radium is an alpha emitter. It spits out alpha particles, and it turns into radon. Now, a story about radium. My sister was born with very pale skin, blue eyes, blonde hair, and a big red birthmark right on her cheek. And my parents were totally freaked out about that. And this is about 1955. And, you know, nuclear chemistry, it's pretty young. So a guy in New York City said, I can get rid of that without having surgery. And my parents said, great. And in 1955, it took about 6 hours to get to New York City by car. And so they went down there, and what this doctor did is he had a cube of radium, and he taped it to my sister's cheek where the birthmark was for about 15 minutes, then took it off. We drove home. We did that 3 times, back and forth. And eventually, after 3 times, the birthmark was gone. And everybody was happy. Well, you have to remember this. Radiation causes cancer, and it also cures cancer. 2 weird things. It does both. And how does it cure cancer? It kills rapidly multiplying cells, like the tumor cells. Well, my sister was only about 5 or 6 years old when they strapped the cube to her cheek. And radiation kills rapidly multiplying cells. That's why, girls, if you ever go in for x-rays, the first question they ask you is, are you pregnant? Because if you're pregnant, you can't get x-rays, because x-rays kill rapidly multiplying cells. And there's nothing more rapidly multiplying than an embryo. So, about a year or 2 later, after my sister had that birthmark dissipated by the radium, she was getting her adult teeth. Well, guess what? None of her adult teeth where that cube of radium was taped on came in. She's missing 2 molars on top and 2 molars on the bottom. Why? Because that radium killed rapidly multiplying cells. And her teeth were rapidly multiplying cells, the adult teeth were, and they never came in. So she's got 2 fake teeth on top, 2 fake teeth on the bottom, but she's 2 years younger than I am, and she's still doing fine. So those are the 2 stories. So remember, alpha particles, if you breathe them in, could be dangerous. And if you have some crazy material like radium stuck to your cheek, it could cause damage. And we're going to talk about who discovered radium a little while later. Okay, so we're going to do one more alpha decay. Remember, if it's an alpha emitter, mass down 4, number down 2. So this one, is francium-220, and the atomic number is 87. And once again, if it's an alpha emitter, it spits out an alpha particle. So the new radioisotope that's formed, down 4 in mass, down 2 in atomic number. So we go down 4 in mass, that's 216. Down 2 in number, that's 85. And that is AT. Okay, so those are 3 examples. I'm going to give you 2 examples to do and to email me in. So we're probably going to be doing, you're probably going to have 10 of these to do and email me in, okay? So here are 2 that I want you to finish, and these are pretty easy. So number 1 to email me in. The first alpha decay is uranium-238, 92. That undergoes alpha decay. The second alpha decay, So the second alpha decay I want you to do is thorium 23290. Don't forget, alpha decay means the radioisotope spits out an alpha particle, atomic mass down by 4, atomic number down by 2. So those are the first two that you should send me. Next. So that's alpha decay. So you know what an alpha particle is? It's huge, like a bulldozer. It moves very slow. The penetrating power isn't very much. Stopped by skin and clothes. But if you breathe it in, it could be deadly. And it's got a positive charge, and it has a mass of 4 AMU. Okay. The next thing, this is capital B. These are beta particles. And on here, on reference table N, again, a beta particle is this. A B with a tail on it and a negative sign. That's what a beta particle symbol is. Remember, alpha particle is like that fat fish swimming to the left. A beta particle is a B with a negative on there. Now this is very interesting because a beta particle is nothing other than this. A beta particle is a high-speed electron. So what's the symbol? This. E0 minus 1. So that's the symbol of an electron. The 0 up there means there's no electrons in the atomic mass. The -1 means whatever the atomic number is, you just put a little negative there. And that's how many electrons. So, beta particles are high-speed electrons. Number 2. Obviously, they have a negative charge. And they have hardly any mass. So remember I told you, you got to think about an alpha particle as a bulldozer, really big, but very slow. Well, the way to think about a beta particle is, it's a cannonball. So cannonballs are only about this big, much, much smaller than a bulldozer, but they're much faster. So you have alpha particles a bulldozer and beta particles a cannonball. Now, you know cannonballs go very quick, and so their penetrating power is much greater than alpha particles. So beta particles can be stopped by a book, you know, about that thick, or a table, a piece of wood, anything like that. Now, these will penetrate skin. Okay, so we're going to be talking about all this later, but we might as well talk about it now. When the nuclear reactor blew up in Chernobyl in Russia, firemen were called to the scene to put out the fires. The problem is, nobody told the firemen that there was radioactive material on fire. And the radioactive material was giving off beta particles. Now, these beta particles penetrated their firemen's clothing. And they don't feel anything. It's not like getting hit by a bullet or getting knifed or anything like that. If you're hit by radiation, you don't feel it until later. So after they put out some of the fires, not all of them, they went back to the firehouse. They took their heavy-duty clothes off, and they looked, and they found that their skin had turned brown. And they're going, looks like I have a suntan. And a little bit later on, after their skin turned brown, their lips and tongue started turning brown, and then their skin turned black along with their lips and tongue, and their skin died. And if your skin dies, you die. So those firemen all died that put out the fires because of these beta particles. And it's called this. Number 5. A nuclear suntan. Oops. So a nuclear suntan is due to getting hit by tons and tons and tons of beta particles. And it is lethal. It will kill you. All right, so now we have this. We got the bulldozer alpha particle, doesn't penetrate too much. We have the cannonball beta particle, very quick, penetrates more, but they're much smaller than the alpha particles. All right, now we had alpha decay as the first type of natural transmutation. This is the second type of natural transmutation. This is called beta decay. So we're going to put an asterisk. We're going to write down beta decay. Now all we have to do is look on reference table N to see what radioisotopes decay by spitting out beta. And let's do cobalt 60. So we're looking for cobalt, that's 27. Now watch what happens. Remember, alpha decay spit out a helium nucleus, and it went down 4, down 2. Beta decay spits out a beta particle. And remember, a beta particle is simply a high-speed electron. So the atomic mass on the left got equal to the atomic mass on the right. Atomic number on the left got equal to atomic number on the right. So 0 atomic mass. So 60 over here. The new radioisotope is going to have a mass of 60. That's 27, but that says -1. And if there's 27 on this side, there's got to be a total of 27 on that side. So we got to put 28. Because 28 minus 1 is 27. So here, the atomic mass stayed the same for beta decay, but the atomic number went up by 1. So 28 happens to be nickel. So, in beta decay, the atomic mass stays the same, and the atomic number goes up by 1. And remember, that nickel isn't a stable element. That's a radioisotope. That's radioactive nickel. Okay, so that's one of the beta decays. We're going to do 2 more, and then I'm going to give you 2 to do. Remember, at the beginning of this lecture, I gave you 3 isotopes of hydrogen, and I said that one, H3, is radioactive. So that spits out a beta particle. So let's see what's left. We're going to have 3 there, that's 0, so 3 mass. And then if that's 1, and that's a -1, this has to be 2. 2 minus 1 is 1. And what has the atomic number of 2? Helium. But don't forget that helium is going to be a radioisotope. It's going to be radioactive. All right? One more, then I'm going to give you 2 to do. This is Tactinium 99. So let's look for TC. And it's 43. All right. Tactinium 99 is a beta emitter, so it spits out a high-speed electron. So the atomic mass stays the same at 99. And the atomic number has to go up 1, so it's 44. 44 minus 1 is 43. So what's 44? Ru. So those are 3 examples of beta decay. Now I'm going to give you 2 to do. So I have question 1 and question 2. This is going to be question 3 and question 4. Cesium 137, and let's look for the atomic number for cesium. It's 55. So you're going to do cesium 137, 55. You're going to do a beta decay on that. And one of the most important ones, like ever, and we'll talk about it later on, is number 4, and that's I-131. That is radioactive iodine 131, and the atomic number is 53. So you have 2 alpha decays to do, and now you have 2 beta decays to do. All right? Okay. Now, the third natural transmutation. We've had alpha decay, we've had beta decay. This is called positron emission. You never heard of a positron. So, a positron, sounds weird, has a symbol of this. It looks like a beta particle, but it is positive. So, a positron is a positive electron. Now, this is very, very weird, but I'm going to show you how a positive electron was formed. So we're going to go like this. So, positron is a positive electron. Now here is what happened. Remember, P11 is a proton. All right, 1 in the atomic number, 1 in the atomic mass. So what happens is this. A proton blows up. All right, it totally explodes, and it gives off 2 products, and I'm going to show you the first one. Now, if a proton blows up and gives you one neutron, there's something else, but look, you got one atomic mass, you got one atomic mass. So the other thing, the other subatomic particle that's blowing out of the proton has no mass. So it's going to be like this. You know we got 0 up here because if we have 1 on that side, we got to have 1 on this side. We already do. There's 0 on this side, 1 there, so this thing has to have this. So, when a proton explodes, it produces a neutron and a positron. That's what happens. So now we have positron emission, which is like alpha decay or beta decay. All right? So we look on this chart, and we're looking for a beta with a plus sign next to it. So we're going to do 2 of these. So the first thing we're going to do is this. We'll put down number 2. So potassium 37 throws up a positron. So it's going to go like this, yields. Positron is a positive electron. So what's left? What is the new radioisotope on the other side? That's 37, that's 0, so this has to be 37. This is 19, there's already 1 over here, so it has to be 18. 18 plus 1 equals 19. And 18, you all know, is argon. Argon. All right? We're going to do 1 more positron, then I'm going to give you 2 to do. And that's going to be iron, 53. And iron, I think it's 26. So all you have to do, and there's only 1 there, so now we have 5 for homework. 2 alpha decays, 2 beta decays, and 1 positron emission. Okay? So, those are the 3 ways that natural transmutation works. Natural means we don't have to do anything. It does it by itself. So we have alpha decay, beta decay, and positron emission. Those are the 3 natural transmutations. But we didn't talk about something. We talked about alpha particles. We talked about beta particles. But we didn't talk about the 3rd emission from radioisotopes, and that's gamma rays. So capital A was alpha particles, capital B was beta particles, capital C is gamma rays. Something weird here. Alpha and beta are particles, and this is a ray. So the symbol for a gamma ray is this. And gamma rays are way different than alpha and beta particles. Remember, I said 3 things can make one radioisotope change into another. Alpha decay, beta decay, and positron emission. This doesn't. So this does not artificially transmutate one radioactive element into another. Well, what does it do? Well, first let's talk about what is a gamma ray. So number 1. First of all, it has no mass and no charge. Second thing is it travels at the speed of light, because it's a ray, it's like a light ray. So if it doesn't transmutate anything, then it must not change the proton number. And if it doesn't change the proton number, it doesn't change the element. So we're going to put an asterisk at number 4. So what does a gamma ray actually do? If it doesn't mess with the proton number, what does it do? Well, here's what it does. If a radioisotope is giving out gamma rays, it's lowering the energy content of that radioisotope. Okay? So for number 4, big old asterisk. That's a big one. It lowers the energy content of the radioisotope. So it gets less and less and less and less the longer the gamma rays are being emitted. Now, remember, alpha particles can be stopped by skin or clothes or anything like that. Beta particles, you need something a little bit thicker, like maybe aluminum foil or wood or a book. It won't stop with skin or clothes. Gamma rays, these things are incredible. Here's what you need to stop a gamma ray. You need at least 6 inches of lead, or you have to be underground over 30 feet down, or you can have about a 6-foot thick reinforced concrete and steel structure. That would stop it. But a school building, it would go through one wall, it would go through all the students, go through the other wall. Remember, these are really dangerous because radioactive particles that hit you kill cells. That's how it works. So, lowers the energy content of radioisotopes, stopped by 6 inches of lead or 30 feet of dirt or like 6 feet of reinforced concrete and steel. But it doesn't change the proton number, so it doesn't transmutate. So just remember for this lecture, 3 ways to artificially transmutate a radioisotope: alpha decay, beta decay, and positron emission. Okay.